You know, it's kind of funny how we picture windmills. Sometimes, maybe big, noisy things. Maybe even bad for birds.
That perception is definitely out there.
But here's a thought that flips, that in India, wind power really picks up during the monsoon.
Yeah, exactly when solar energy kind of takes a dip because of the clouds. It's a neat synergy.
Okay, let's unpack that. Welcome to the deep dive.
Today we're diving into wind power, a key renewable, right?
Absolutely. And our main source today is Lecture 14 from Professor Pushpito Ghosh's Renewable Energy Resources course at ICT Mumbai.
That was GTT 2105, part of a series from 2021, and listeners can find the whole thing on YouTube if they want the really deep version.
Right. So our mission for you today, get the core ideas, the principles, the applications of wind power that Professor Ghosh laid out, quick but thorough.
We'll be touching on the benefits, how wind even forms, what affects its speed.
The global picture, India scene, how turbines work, design stuff, basically pulling the key insights from that lecture.
And Professor Ghosh kicked off with a really fundamental point, self-reliance.
Ah, yes. Energy independence.
Exactly. Every bit of energy from wind is energy we don't import. Think about that strategically for India's security. It's huge.
Totally. And then there's the obvious environmental wind, right? No fossil fuels, no emissions, just clean energy.
A literal breath of fresh air, as you said. And he also mentioned it's somewhat distributed.
Yeah, though he did point out that Western and Southern India have, much better potential than other parts. It's not perfectly even.
Which is interesting when you think about India's energy map, like where the coal reserves are concentrated more in the east.
Right. So how do you balance using what's there versus pushing for cleaner options everywhere, especially when wind potential varies so much?
It's a major planning challenge.
And something else maybe surprising, wind power itself, relatively quiet, like solar panels.
Yeah, the main sound is the whoosh of the blades, but it's not like industrial noise pollution usually.
Although Professor Ghosh did mention that general perception about birds.
Right, the idea that windmills drive them away. He said he couldn't actually confirm if it's true, scientifically speaking, but he acknowledged people believe it.
And that perception matters, doesn't it? Even if it's anecdotal, it can shape public opinion policy.
Absolutely. Clear communication about the actual impacts is key for adopting any new tech.
Okay, so let's get fundamental. What actually makes the wind blow?
It all comes down to pressure differences. High pressure zones, low pressure zones in the atmosphere.
And those pressure zones are caused by
Temperature differences, that's the root cause. Land heats differently than water. Different parts of the globe get different amounts of sun.
So ultimately, the sun is powering the wind. It's all solar energy, in a way.
Precisely. The uneven heating is key. Like during the day, land heats up faster than the sea.
Creating low pressure over land, high pressure over the cooler sea.
And boom, you get the sea breeze blowing inland.
Then at night, it flips. Land cools faster, becomes higher pressure, air flows out to the relatively warmer sea, the land breeze.
It's this constant cycle, this convective movement, redistributing heat around the planet.
That it's not just straight lines of air moving, is it? The Earth's rotation messes with things.
The Coriolis effect. It makes the wind curve. Think about trying to roll a ball straight across a spinning merry-go-round. It looks like it curves, right?
Right.
So in the northern hemisphere, that leads to cyclones spinning in the direction of Earth's rotation and anticyclones the other way.
And it's the opposite in the southern hemisphere.
Exactly. It's a fascinating interplay of thermodynamics and planetary physics.
Okay, so we have wind, but the speed we feel isn't constant. Professor Ghosh talked about height.
Yeah, wind near the ground gets slowed down by friction.
Yeah.
Buildings, trees, terrain. It's like drag.
Like wading through something thick near the bottom.
Good analogy. The higher you go, the less friction, the faster the wind.
And the pressure gradient itself matters too, right? How close the highs and lows are.
Definitely. A steeper gradient, meaning high and low pressure areas, are closer together, means stronger winds. It's trying to equalize faster.
And the flow isn't direct, you said. It spirals along lines of constant pressure.
Exactly, along isobars. That rotation effect makes it flow in these complex, swirling patterns. It's not just a straight shot from high to low.
Wow, okay. No wonder weather forecasting is so hard and needs those supercomputers.
It really is complex fluid dynamics on a massive scale.
But he also mentioned some terrain can actually help, like convex hills.
That's right. Rounded hilltops can sort of funnel the airflow. The wind lines get squeezed together over the top, accelerating the wind.
Ah, so that's why you often see turbines right on top of hills or ridges.
Precisely. It's using the natural landscape to boost the available energy. Smart siting.
Which leads to the whole idea of siting windmills. It's not just finding a windy country, it's the specific spot. Hills, coastlines for those breezes.
Yeah, local geography is critical. Professor Ghosh mentions seeing, thousands of windmills between Porbandar and Dwarka in Gujarat,
Right on the coast.
and lots in Tamil Nadu too. But fewer, he noted, in Maharashtra, for instance. It really shows the regional differences within India.
And the height of the tower makes a big difference, capitalizing on that faster wind higher up.
Definitely. He even gave a formula to estimate it. Visi equals VR times. The natural log of z over 0 divided by the natural log of 0 over 0.
Okay, let's break that down. V is the speed you want at height z. VR is the known speed at a reference height 0.
And z0, that's the key part, the roughness length. It's a measure of how bumpy or obstructive the ground is.
So like open sea would have a really low 0, smooth.
Very low, minimal friction, farmland with a few trees, a bit higher, a suburb with lots of buildings, much higher z0, more drag.
He gave an example, didn't he? 8 meters per second at 20 meters.
Over farmland with 0 of zero point 0.1 meters, and he calculated the speed at 50 meters would be about 9.38 meters.
So a decent jump just by going up 30 meters.
A significant increase, but there's a catch, as I pointed out with the graph.
Diminishing returns.
Exactly. The wind speed increases with height, but the rate of increase slows down. Going from, say, 200 to 300 meters might not give you as much extra speed as going from 20 to 120 meters.
And building super tall towers gets really expensive.
Very expensive. So there's an economic trade-off between tower height, cost, and the extra energy you capture.
Makes sense. Okay, so how do we classify how good a wind site is? Professor Ghosh mentioned wind power classes.
Right. 7 classes based on average wind speeds, usually measured at 10 meters and 50 meters height.
And also based on wind power density, watts per square meter.
Yep. It tells you how much power is flowing through a given area. And the crucial thing to remember is the power goes up with the cube of the wind speed.
Not linear. So a small speed increase means a big power increase.
A huge difference. That's why even going from class 3 to class 4 represents a major jump in potential energy generation.
He compared peak wind power density to peak solar radiation, which was an interesting analogy. Puts the energy potential in perspective.
It does. Now, looking at those global wind maps he showed, quite revealing.
Yeah, lots of strong winds over the oceans, those lighter colors. And over land, the brownish areas are windier, bluish, less so.
Some real hot spots pop out, parts of the oceans, Greenland's tip, southern South America.
And then zooming in on India,
Mm-hmm.
mostly moderate speeds, right? Concentrated along that western coast.
Primarily. Gujarat, Tamil Nadu show up well, but large parts of central and eastern India looked less windy on that map.
Which explains his point about maybe not putting huge wind farms everywhere in India. Focus where the resource is strongest.
Compared to, say, China, which the map showed having much more extensive high wind areas on shore.
Okay, let's talk about India's actual setup. Around 97 gigawatts total renewables installed now.
Roughly, yeah. And wind is about 40 gigabayu. Of that, solar's just overtaken it slightly at 41 gigaW.
That's a shift. Wind used to be the leader for a long time.
It did. Professor Ghosh showed the growth from about 23 gigabayus in 2014-15 up to around 39-40 GW more recently. Steady growth.
But the actual generation isn't 100% of capacity, obviously. He mentioned the utilization factor.
Right, the capacity utilization factor, or CUF. Based on 2021 numbers, it was around 17.6% for wind in India.
So installed capacity is one thing, actual electrons generated is another, heavily dependent on how much the wind actually blows.
And when it blows. That seasonal aspect in India is fascinating.
The monsoon peak. June to September is when most of the wind generation happens.
Which, as we said, perfectly complements solar, which struggles a bit in the cloudy monsoon.
It's such a neat natural synergy. Makes you think about hybrid projects.
Definitely. Co-locating wind and solar could make a lot of sense, especially since windmills need quite a bit of space around them anyway. Use the land efficiently.
Globally, we're looking at around 600 GW of installed wind capacity.
Somewhere around there, yeah. India's share was about 6% back in 2018 data, likely similar now.
But Professor Ghosh's point was key. Lower average wind speeds here mean our 40 GW might not produce as much electricity overall as 40 GW in, say, windy parts of the US or China.
Exactly. Productivity per installed GW matters. China is the big leader, by far, in total capacity. Then the US, Germany, India, UK.
And within India, the leading states he listed, Tamil Nadu, Gujarat, then Maharashtra, Karnataka, Rajasthan, AP, that matches the wind maps pretty well.
It lines up nicely with where the better wind resources are located.
He also briefly mentioned pumped hydro storage. using excess wind power to pump water up.
Yes, storing energy as potential energy in a reservoir, like a giant battery. Then release the water through turbines when you need power.
Like at Niagara Falls, they do that.
It's a well-established storage method. Could be interesting to explore more links between wind projects and existing hydro dams in India.
Okay, let's get into the machines themselves. How do turbines actually capture wind energy? Two forces.
Lift and drag, those are the key aerodynamic forces on the blades.
And most turbines we see, the horizontal axis ones, they mainly use lift.
Primarily, yes. The blades are shaped like airfoils, like airplane wings. The wind flows faster over the curved top surface, creating lower pressure there compared to the bottom. That pressure difference generates lift, perpendicular to the wind direction, which makes the rotor spin.
Drag is the force pushing along with the wind.
Right. Less important for horizontal axis turbines, but more so for some vertical axis designs.
Gotcha. He walked through the components too, didn't he? From the ground up.
Yep. Foundation, grid connection, the tower itself.
Often with a ladder or lift inside.
Then the yaw control up top, which turns the whole nacelle to face the wind.
The nacelle being the big box, housing everything.
Exactly. Generator, gearbox, brakes, control systems, all inside the nacelle.
Plus an anemometer outside to measure wind speed.
Crucial for control. Then you have the rotor itself, the hub, and the blades.
And the blades can change their angle. Pitch control.
Right. Pitch control adjusts the angle of the blades to optimize power capture in different wind speeds, or feather them to stop in very high winds.
So wind spins the blades, the rotor turns a shaft.
Yeah, that shaft usually goes into a gearbox to increase the rotational speed.
Because the blades turn relatively slowly, but generators need high speed.
Correct. Low speed, high torque from the rotor becomes high speed, low torque for the generator.
And the generator uses electromagnetic induction to make electricity.
That's the basic principle. Mechanical rotation into electrical energy.
What about those vertical axis ones? They look different.
They do, like egg beaters sometimes. The main advantage Professor Ghosh mentioned is the heavy stuff generator. Gearbox can be at ground level. Much easier for maintenance.
Oh, makes sense. No climbing 80 meters up a tower.
But they are generally less efficient and less common for large-scale power generation.
Okay, blade design. Length matters. He's talked about tip speed.
Yes, the speed of the very outer tip of the blade as it rotates.
And the tip speed ratio.
That's the ratio of the blade tip speed to the actual wind speed. There's an optimal ratio, theoretically around 6, for best performance.
Why is that important?
It relates to how efficiently the blades extract energy. Too slow, you miss power. Too fast, you create turbulence and lose efficiency.
He had an example calculation based on that ratio, wind speed and desired RPM.
To figure out the ideal rotor radius R, and showed how it differed for, say, a one-blade versus a three-blade design to hit that optimal tip speed ratio.
And once you have the radius R, you get the swept area, A equals pi R squared.
The bigger the circle the blades sweep, the more wind they intercept.
Which brings us back to the power equation.
Yeah.
Power depends on that swept area, A.
And crucially, wind speed cubed, V cubed.
Right. He put it all together in a practical formula.
Yeah, power equals of air 0.5 times air density times swept area, A times wind speed cubed, V3.
Times a bunch of efficiency factors.
Exactly. The coefficient of performance, CP, which is how much power the blades can actually extract max theoretical, is 0.59, Betz's limit. But practical is more like 0.3 to 0.35.
Okay.
Then generator efficiency, maybe 80% or 0.8. And gearbox efficiency, maybe 95% or 0.95.
So you multiply all those together to get the actual electrical power output.
Pretty much. It shows how each component's efficiency impacts the final result, but that V cubed term for wind speed dominates everything.
That's the biggest lever. He also mentioned a cool innovation linking a windmill directly to a pump.
Yeah, for seawater desalination using reverse osmosis. Working with Sardar Patel Institute. Bypassing the electricity generation step for certain applications could be more efficient.
Interesting idea.
So, wrapping up this dive into Professor Ghosh's lecture, what are the big takeaways?
Well, that wind speed cube relationship is huge. Location matters immensely because of it.
Definitely. And the uneven distribution of good wind sites, particularly in India, focusing on the west and south.
Plus that really neat complementarity with solar, especially during the Indian monsoon.
A vital synergy for India's renewable mix. And understanding the basics of how turbines work lift, the key components, the efficiencies involved.
He gives you a much better appreciation for those giant structures. So here's a final thought to chew on. Given that India's wind power peaks during the monsoon, complementing solar, What kind of truly innovative energy storage solutions beyond just pumped hydro could we develop to really maximize this dynamic duo and smooth out the power supply year-round?
That's a great question. Better, cheaper, longer duration storage is definitely a key challenge for a high renewable future. Something to think about.
Absolutely. And if you want to dig even deeper into the physics and engineering, remember Professor Ghosh's full lecture, Lecture 14, is out there on YouTube. Worth a watch.